In the last video, we talked about potential energy stored in a capacitor. We do work moving the charges from one plate to the other, separating the charges, and that creates an electric field between the plates. And if we hook that capacitor up to a light bulb or some other device, the charges will move back to the original plate through our device and we can get some energy out of it. That's stored energy, or electric potential energy. The potential energy in a capacitor is 1/2 Q delta V. And because we know something about capacitors, we can use Q equals C delta V and substitute in and come up with other forms for our electric potential energy of a capacitor. All of these are equivalent. Now, we've been dealing with capacitors, and we haven't really talked about what's between the plates. We've made the assumption that there is nothing between the plates of the capacitor, basically a vacuum, a void. But it's hard to manufacture that. It's much easier to take a conductive plate, put some kind of an electrical insulator there, and then set another conductive plate on top of it. It makes a much easier manufacturing process. It's more durable. You know your conductive plates will never touch each other, because if they do touch each other, if there's a conductive path from one plate to the other, you don't have a capacitor anymore. The charges will go back to where they started, and you won't have any energy stored. When we put an electrical insulator between the plates of a capacitor, it has an effect on the capacitance. It has an effect on the electric field, and we haven't talked about that yet. So let's do it now. The fancy word for an electrical insulator is a dielectric. Let's take a look at what happens when we take a parallel plate capacitor and put a dielectric, or an electrical insulator, between the plates. Here's my capacitor after I've hooked it up to a battery, and the battery did work moving the charges from one plate to the other, separating the charges. One plate is positively charged, the other plate is negatively charged. Now I'm going to fill the space between these plates with an electrical insulator, a dielectric material. If we could zoom in on the atoms and molecules that make up this dielectric material, they are now sitting in a strong electric field that points from the positive plate to the negative plate. What happens to the electron cloud around the atom? It gets shifted a little bit, right? The positive core is pulled one way in the electric field. That's the nucleus of the atom, is the positive part. It gets pulled one way in the electric field. The negative electron cloud gets pulled the other way, and our atom becomes slightly polar. One side is a little bit more positive, and one side is a little bit more negative. So if I could zoom in here and picture what the atoms and molecules look like. So there's my first molecule, or atom, with the electron cloud and the nucleus pulled in opposite directions. One side slightly negative, one side slightly positive. And this happens all throughout the dielectric material. You get the idea. What I've drawn is a dielectric material that's only 3 molecules across. We know, of course, there are many, many molecules that would make up this dielectric material. And if we look at what's going on in here, basically all the charge cancels out. We have some excess positive charge from one, some excess negative from the other. Basically, in the center there, the charge sort of all cancels out. And what we're left with is a left surface here near the positive plate, the dielectric material near the positive plate, has excess negative charge. And the surface on the other side, the right side, near the negative plate, has a net positive charge. So we're creating a negative surface on the dielectric near the positive plate and a positive surface on the dielectric near the negative plate. As you can see here, we've got those excess negative charges there, and on this surface, we've got the excess positive charge. Let's take a closer look at what's happening between the plates of the capacitor. If the dielectric was not there, we would get a big electric field between the positive plate and the negative plate. And let's call that E plates. The electric field created by the charges on the plates of our capacitor. But we also have these charged surfaces on our dielectric, and they're going to create electric field in the opposite direction. We'll call that E dielectric. We've got a big electric field caused by the charge on the plates, and we've got a smaller electric field caused by the charge separation that's built up on the surface of our dielectric. What does that do to the net electric field between the plates? It reduces it. So the net electric field is going to be less than the original electric field I had between the plates when the dielectric was not there. And what does that do to the capacitance of our capacitor? Remember, the capacitance is the proportionality constant in our equation Q equals C delta V. If there's less net electric field between the plates, then it's easier for the battery to push charges against that field to the other side. So the same battery, the same delta V, can move more charges from one plate to the other. Our capacitance increases when we put a dielectric between the plates of our capacitor. This is the equation we found for the capacitance of a parallel plate capacitor before we knew about dielectrics. And now we'll make it complete by adding the dielectric effect. This is called the dielectric constant, kappa. And it is always greater than or equal to 1. It's 1 for a vacuum, and it's almost 1 for air, very, very close, and it increases with other dielectric materials. So as we put dielectrics between the plate of our capacitor, solid electrical insulators, well, not always solid. Sometimes they use liquids in capacitors that act as the dielectric material. So in general, we can write this relationship. The capacitance of a capacitor is equal to the capacitance without a dielectric, with just a vacuum between the plates, multiplied by the dielectric constant.